Assalamu alaikum. So let's continue with the DC motor drive. Now, in general, in order to control the speed, we end up with controlling the voltage either in the armature, and this will is the armature voltage control, in which we are controlling the speed below the rated speed, or the flux control. Also, we need to control the feed voltage by reducing the the voltage in order to weakening the flux in order to increase the speed. So to do so, we need power electronics. So for example, the first thing here we'll discuss is the controlled rectifier fed DC drive. And this is limited, let's say, to 15 kilowatts. So this one, the first thing here we'll discuss is the controlled rectifier fed DC drive. So the first thing here, let's assume that we have the machine. Now we need to control the armature voltage of the machine. So we'll use a controlled rectifier, and it can be single phase or three phase. Let's assume that we are using here a three phase controlled rectifier, and this is the controlled rectifier in which we are using a thyristor as switch. Now, in order to control, we need speed control, and we need a current control or a torque control. So here we will use a controller. It's control unit, let's say. And this take the information. It will take the current information. So here we can measure the current. And here we can use a tacho generator, and the tacho generator can be seen as a parent magnet DC generator, for example, or a parent magnet DC machine. So this is the tacho generator, tachometer we can call it, or speed sensor, and this will be the speed information. So here is the speed, and this is the current. The control unit will generate the thyristor gating or firing. So here this is the control unit, and let's say the SCR firing unit, which will give the firing angle or the gate pulse for the switch. And for the control unit, we need the speed command. So let's assume this is the speed command. So here now we're having a variable DC supply. It can be controlled by controlling alpha here, the firing angle. And for the field, also, it can be controlled using a controlled rectifier. Let's assume this one is a single phase, and here we need the firing angle for the field and the firing angle for the armature circuit. So this is the circuit diagram. We can plot the equivalent circuit here. Let's assume that we are using three phase full controlled rectifier. Now here is the the machine is connected. This is plus minus VA, which equal VDC, and here we have the three phase. Call it RST, call it VA, VB, VC. So this is the three phase. Now this is a thyristor. It's a unidirectional switch. It will conduct if the anode is more positive than the cathode, and if there's a gating or holding current enough to open the gate. And this will be the direction of the current all the time. This will be IA. Now for the field, this is the field. Let's assume that we are using a controlled rectifier, single phase. This is a single phase here, and here plus minus VF, and this will be the IF. It's also unidirectional. Now here, if we drive the relation between the firing angle and between the input voltage and the DC voltage, we will end up with, in the case of the three-phase system, for three-phase rectifier, VA will equal to 3 square root of 2 V line to line over pi cosine alpha. Simply, this can be written for simplicity 1.35 V line to line RMS value cosine alpha. Which alpha? Alpha A, because I'm assuming that I'm using a three-phase rectifier in order to control the armature. For the field, it's a single phase. For the field, it's a single phase. So simply here, we're having VF is equal to 2 Vmax over pi cosine alpha F. Now, if I need to plot this one or this one as a function of the firing angle, so this is alpha, and this is the voltage, VA. Now, let's assume that I'm plotting the single phase, so V will equal 2 Vmax over pi cosine alpha. So when alpha equal to 0, we'll have the maximum, which is 2 Vmax over pi, and so here at alpha equal to 0, we will have V max, which will equal 2 Vm over pi, or Va, let's say. Now, at alpha equal pi over 2, then Va will equal to 0, pi over 2. Here I'm having the 0. And at pi, and at alpha equal to pi, we'll have the minus. Va will equal minus 2 Vmax over pi. So if I need to plot it, it will be something like this. So here the voltage is positive, here the voltage is negative. And remember, because we are using a unidirectional switch, all the time the current will be positive. So simply this means that this one can operate in Q1. If I recall here, this is the torque, this is the speed, this is the Q1 when the torque is positive and the speed is positive, and this is the Q2 when the speed is positive and the torque is negative, and this is Q3 when the torque and the speed are negative, and finally here Q4 when the speed is negative and the torque is positive. Now we know that the torque is proportional with the current IA. So if the current all the time positive, this means that we are working either in Q1 or Q4 according to the voltage sign. So simply this means that if the voltage is positive, I'm working in Q1. If the voltage is negative, I'm working in Q4. So how I can do the 4-quadrant drive? This only support 2-quadrant drive, and simply I cannot go from Q1 to Q4. Unfortunately, if I need to go from Q1 to Q4, I need to go to Q2, then Q3, then Q4. So simply we need a mechanism in order to support the 4-quadrant drive, which means that I need the mechanism to allow the power flow in multi-direction. So for that, let's see. Now each rectifier, the current is already governed by the direction of the switch, and the voltage can be positive and negative. So my problem now in the current direction. So in order to reverse the current direction, I need to reverse the switch. So simply this means that if I need to do the 4-quadrant drive, I need to connect 2 converter in anti-parallel configuration. So here for 4-quadrant, drive, we need to use 2 converters in anti-parallel configuration. For simplicity, let's assume that here I'm having a single phase full wave rectifier, and this one here is connected to the armature. Now I will connect another converter, but this one in opposite direction, in anti-parallel direction. And let's assume also it's a single phase. It's supplied from the same supply, by the way. It's supplied, or we can supply it from the phase, or it should be supplied from the phase supply. So now this will be converter number 1, and this will be converter number 2. So this will be converter number 2. So here I need to supply alpha 2 for it, and this will be converter number 1, which also I need to supply alpha 1 firing angle number 1 for it. So now, under the sense of the direction, this will be the plus minus for the first converter, and this will be the plus minus for the second converter, V2. Now, in order to avoid short circuit or circulating current in the power electronics, alpha 1 and alpha 2 must be specified such that V1 plus V2 is equal to 0. So if we do so, now converter number 1 will support Q1, will support Q1 and Q4 operations, while converter number 2 will support Q2 and Q3 operation. Why? Because the voltage can be positive or negative, But here the current is negative. So if we recall the torque speed characteristic, all the time the current is negative, so simply I end up working either in Q2 or Q3. So in order to avoid short circuit or what we call circulating current in the inverter, V1 plus V2 must equal to 0. So from here we can end up with cosine alpha 1 plus cosine alpha 2 must equal to 0. Now we can use trigonometric identity. Of course here I'm neglecting the constant, which is 2V max over pi, because in the end of the day I need it to equal to 0 all the term. So I will end up with cosine alpha 1 minus alpha 2 over 2 multiplied by cosine alpha 1 plus alpha 2 over 2 must equal to 0. So in order to make it 0, then this term must equal to 0, which means that alpha 1 plus alpha 2 is equal to pi. And why I'm not selecting that one? Because the maximum of the angle is equal to pi. So if I'm selecting this one, this would be alpha 1 minus alpha 2 is equal to pi. So alpha 1 will equal pi plus alpha 2, which means that one of the angle will be greater than pi, and this is not possible because here we already having that the variation of the angle is from 0 to the pi. So simply this means that alpha 2 will equal pi minus alpha 1. So simply if I specified alpha 1, automatically I can take the complement and find or calculate alpha 2, and I can calculate alpha 2. So for summary here, we can summarize here that this is the torque speed characteristic curves. This is the torque, this is omega. Now here we have Q1 and Q4 for the first converter, and here we have Q2 and Q3 due to the second converter. Now here the voltage is positive, so Q1 is taking the advantage, so alpha 1 must be greater than 0 less than 90, and automatically alpha 2 will equal pi minus alpha 1. So let's use pi over 2 here. Now for a Q number 2, we'll have alpha 1 is greater than pi over 2 less than pi, and alpha 2 is equal pi minus alpha 1. For the second converter in Q2 here, we'll have that alpha 2 is greater than 90 less than pi, and alpha 1 is equal pi minus alpha 2, and finally here in the Q3 alpha 2 is greater than 0 less than pi over 2, and alpha 1 is equal pi minus alpha 2. And this is if we are using the let's say the controlled rectifier. Sometime, or it's better, let's say, to use discrete switches like MOSFET, IGBT, GTO in order to control the DC drive, or let's assume that the supply is DC. If the supply is DC, in this case, I cannot use a rectifier because the rectifier will convert the AC power to a DC power. So this is AC power and this is DC. That's why here we will use a rectifier. And if the supply is DC, or simply if we don't have controlled rectifier, we have uncontrolled rectifier, let's say bridge rectifier. Here we will have a DC plus minus V DC. Now this one has a ripple, that's why here we'll use a filter in order to regulate and maintain the DC to be fixed, and after that we'll use the chopper in order to control the DC value. So this is a configuration. Here we have a single phase. Here we have fixed DC. Here we'll have a variable DC. And this, what we call it, a chopper. And this is the uncontrolled rectifier. And this one we call the DC link. And simply here, why we are using capacitor, because if this one single phase, will end up with the following output. It has a ripple. So if we use a capacitor, it can flatten and fix the DC value. So the same thing here. We can use the chopper in order to control the DC drive. So simply this will be a review for the chopper controlled DC drive. Now the first thing here, we'll discuss the two quadrant. Control. So in this case, we're having two switches. And let's assume this switch number 1, this switch number 2, and we're having two anti-parallel diode, and this is, let's call it D1, and this, let's call it D2, and this will be plus minus VA, and this will be the IA. Now here, all the time, the voltage is positive. This plus minus V DC. So now in order to find the mode of operation, let's discuss it using the current. Now in the first scenario, if the current is positive, for positive current, IA greater than 0. Now if IA greater than 0, simply this means that S1 is on and VA will equal VDC, and the current IA will start to build up. Of course, if S1 is on, S2 must be off, because we have a leg, and as the inverter we should avoid the switches in the leg to be operated at the same time, which means that S1 plus S2 must equal to 1, which means that if S1 is on, S2 must equal to 0. Now this is the first scenario. So simply here, if we plotting the output, now let's assume from here to here, this one is T on, the switch S1 is on, so the output will be VDC. Now we have also another condition when the current IA is positive, is that if I2 is conducting. Now also IA greater than 0 if D2 is conducting. Which means that it's freewheeling. The current is freewheeled via the switch. In this case, and this is from T on to the period, the chopping period. So in this case, VA will equal to 0 and IA will start to decrease. So if this one here, the T, and this will be from here to here T on, and from here to here, this will be T off, and we know that T will equal T on plus T off. Now if I need to find the average value, VA average, it will equal T on over T multiplied by VDC, and this what we call the duty cycle of the converter. So this one is D, the duty cycle, which equal T on over T. So this actually is this converter now is forming from S1 and D2. So S1 and D2 actually is acting as a buck converter. So we can write it here. This is the S1 and the D2, and this is actually the buck converter. So VA will equal D VDC, and D will equal T on over T, which means that all the time VA is less than or equal VDC. So if we need to plot VA as a function of the duty cycle, when the duty cycle is equal to 1, then VA will equal to VDC. So all the time VA is less than or equal to the input, and that's why we call it the buck converter. Now let's discuss the second scenario when the current is negative. For the negative current, and let me plot it here. And let me use different colors. This will be the S1, the D2, and this will be the S2 and the D1. Now for the negative current, when IA is negative, this means that either S2 is on or D1 is conducting. Why? Because the current is negative. If the current is negative, it cannot go via S1 or D2. It has two paths, either via D1 or via S2. So the first thing, when IA is negative, this is S2 is on, and if S2 is on, S1 is off. Why? In order to avoid short circuit in the supply side. Now, if S2 is on, simply this means that the current is freewheeling via the switch, and simply this means that VA is equal to 0. If VA is equal to 0, Now the energy will be stored in the inductance. So the energy here. Now part of the energy will be stored in the inductance because there's another part is dissipated across the resistance, the Ra. So here the energy is stored in the inductance La. So if I'm plotting here the T, this is the VA. Now from 0 to T on of the switch number 2, T on switch number 2, the voltage was 0, and when the diode D1 is conducting, the current is negative. Now VA will equal VDC, this plus minus, this plus minus, VA plus will be connected to the plus terminal of the DC, the minus to the minus, to VA, so equal to VDC, and the current will be fed to the supply, and the current will be fed to the supply until here. So let's assume this is the time, and this is the period T. So from here to here, this is the T off, and this is the VDC. Now here the current will recover, or let's say return back to the supply via the D1. Of course, here I'm having a path via D1, and I'm assuming that the supply is accepting power. So the same thing here, if I need to find the average value, V average, it will equal T off over T multiplied by V DC, and we know that T is equal T on plus T off. Of course, here I'm discussing the second switch. Now if I rearrange it, I will get VA average will equal 1 minus D2 multiplied by VDC, where D2 is equal T on of switch number 2 over the period T. And let me plot the active switches here. So now this is the diode, this is the machine, and I'm assuming this is the direction of the current that the machine was running, and we have here certain induced voltage. So this will be plus minus VA and this will be plus minus VDC. So now here the input is VA and the output is VDC. So if we need to write it in terms of the input and the output, so VDC will equal 1 over 1 minus D2 of VA, and this actually the relation for the boost converter. So this means that D1 and switch number 2 is acting as boost converter. So in order to allow a 4-quadrant control, we need to connect another 2 switches in order to allow the current to flow in all the direction and to change the voltage. Now here is the problem is what? All the time the voltage is positive. I cannot change the voltage, you know. The current can be, the direction of the current can be changed, but simply there's a path for the current, but simply all the time here, if this one is positive, this one will be positive. If the input is positive, simply here is positive. So how I can reverse the voltage? I need to have another leg, let's say. So for that, here we'll have the four. So let's discuss the four quadrant control. So let's assume that this is the first switch, this is the second switch. Each switch has antiparallel diode. Now let's connect the machine in between of another two switches. And the antiparallel diode can be either packing with the switch or it can be connected externally according to the switch you are having. So here this is the plus minus VDC, and now here this is switch number 1, D1, switch number 4, D4, switch number 3, D3, switch number 4, D4, and let's assume this is the plus minus for the armature VA, and this is the positive direction or the positive sense for the armature current IA. So here we have two legs actually. So this will be leg A, and this will be leg B. Now the same, if I need to discuss the mode of operation here, I need to discuss for positive current and for negative current. So let's assume that here we have positive current, which means that IA greater than 0, and let's discuss the possible scenario. The first one, S1 and S1 and S4 are conducting. So S1 and S4 are on. So simply this means that VA is positive, IA is positive, and this is the Q1 operation. Now let's see the scenario when the current freewheel via D4 and S2. D4 and S2. Oh, sorry. This is the S2 and this is the D2. So now S2 and D4 are conducting. So now if S2 and D4 are conducting, this means that the current is a freewheel via S2 and D4, which means that VA will equal to 0. Now what else we have? We have if D3 and D4 is conducting, so the current will feed back to the supply. So simply S2 and D4 are conducting, Va equal to 0, and the energy is stored. Energy stored here. Still, we have Q1 operation, by the way. Now, if D3 and D4 are conducting, then VA will equal minus V DC, and the stored energy is returned back to the supply. So the energy is fed back or returned to the supply. So this is the Q4 operation, actually, Q4 operation. So now, this configuration allows us to operate in Q1 and Q4. It allows us to operate as a normal motor, S1 and D2. It allows to freewheel, for example, via S2 and D4 and store the energy in the inductance. And if there is energy that's stored, then we can feed it back to the supply via D3 and D4. Now, what about if we have negative current? Now, for negative current, IA is negative. So here, IA is negative. And let's see what possible scenario we have. The first one is the current will flow via the switch S3 and the switch S4. So simply here, S3 and S4 are on. So VA equal to what? Now VA, this is the positive sense. This is the positive sense. It's connected to the negative, so minus B DC. And the negative is connected to the positive, so this is a minus B DC. And the current increase in the negative direction, so simply this is the Q3 operation. Q3 operation. Because VA is negative and IA is negative. Now, if S4 and D2 are conducting, so S4 and D2 is conducting, so the current is freewheeling via or through S4 and D2, so simply this is energy storing, or store energy, let's say, in the inductance, of course. Now, if there's energy stored and this energy is sufficient to be fed to the supply, then we can go via D1 and D2. So finally here, if D1 and D2 are conducting, the energy is fed back to supply. So energy is fed back to the supply, and this is the Q2 operation. Q2 operation. Now, in order to control, let's say, the machine, we need to have a transfer function or a model for the rectifier and for the chopper. So if we start with the rectifier transfer function, now G rectifier of S can be given as KR over 1 plus tau R S, which is a first order system, can be characterized by DC gain and the time constant. So this is the VC, the control signal, let's say this is the VA, and this is the GR of S, and here KR, for example, for three-phase system, it's 1.35 V line to line over VC max, normalizing. Now tau R is equal to 1 over 2 60 over 360 multiplied by 1 over Fs, the supply frequency. So tau R will equal 1 over 12 multiplied by 1 over Fs. Now Fs is the supply frequency. Now for the chopper transfer function, for the chopper, the same thing, GR of S will equal KR over 1 plus tau R S, except that KR will equal VDC over V triangular, and tau R will equal 1 over 2 FC. Now, here I'm using a pulse width modulation, so this means that, let's assume that I'm doing a current control. This will be the IA reference. I will compare it with the actual current IA. Then here I'm having a PI control, which will give me VC, the control signal. Now this VC, I will compare it to a triangular, which is V triangular, and I will generate the gate pulse for leg A, and the inverted for that will go to leg B. So this actually will be the S1 here, and this will be the S3. And if I need to find S4, I will use that the summation of the S at any leg must equal to 0. So now the last thing we should discuss is the all the time we are using a constant load, but the load can be a non-constant. So simply for the mechanical load, we have TE is constant, and this load is related to lifting, related to let's say crane and so on. So this is a lifting load profile. Now TE proportional with omega, this one is related to the viscous friction, let's say. And we're having TE proportional with omega square, and this is related to the windage load. And finally, we have TE inverse proportion with the omega, and this is related to drilling load. So in general, this is the load torque, TL. So TL can be a combination of those. So TL, for example, can be C, a constant, plus alpha 1 omega plus alpha 2 omega square plus alpha 3 over omega. So this is a general load torque profile. Now what I need to understand is that at steady state, TE must equal TL. Also, for the motor to start, TE must be greater than TL. This is also an important thing in order to remember. Now, this will be not the last lecture, I think, but let's see. So let's assume that this is the last of the DC drive and the DC motor. So stay safe and stay at home.